All right, so I want to explain this paper again. I've explained it in diffusion playlist, but this is a new playlist, Schrodinger bridge, because you don't need to diffuse a data until it comes to noise. You can diffuse it from pi0 distribution to pi1, and pi1 is not trivial. Is again like this can be image data set, this can be blurry version of image data set, or in any modality. So this paper in 2023 by these great people in Oxford University. So solving transport problems has numerous applications. Novel mass transport methods motivated by generative modeling have recently been proposed, like flow matching and all of those. However, it is desirable in many applications to approximate the deterministic dynamic optimal transport, which admits attractive properties. So these flow matching models, these diffusion models, they are not guaranteed to provide transports close to the optimal transport map. But Schrodinger bridge compute the Schrodinger bridges compute stochastic dynamic mapping, which recover entropy regularized version. But the existing numerical methods are either scale poorly or accumulate errors across dimensions. So they introduce iterative Markovian fitting, because traditionally they solve it using iterative proportional fitting that just conditioned on P0 and P1. But here we are not dealing with just distribution at the initial and target. We are our probability is a pass measure. It means that all continuous functions, so we call it a continuous function from 0 to t, final time t, to, for example, I've shown here to r, but it could be rd in rd dimensional. So we are talking about stochastic processes in, but using these path measures. So what is the probability that it is between level A and level B, that you know in financial mathematics, or in control theory, or in diffusion in generative models. So IPF, as I said, is just for these endpoints, but IMF is we want to be on the space of Markov as well as the reciprocal class. We need both of them for the forward and the backward, because we have a reference that as we first create a bridge, like a Brownian bridge, but for a bridge for any general STE, like any drift like F plus sigma dw. This is a Brownian motion. And so let's see. But what is path measure? As I said, is continuous function, space of continuous functions from 0 to t. And so an example of path measure for STE can be seen as, so the solution is random continuous trajectory. Its law is a path measure. Because for any cylinder that you say, different time t1, tn, the joint one, the probability that the joint one is inside a set, we call it the probability of A. So it is on the probability is on the space of paths. And so let me review Doob-Edge transform. It's a huge topic in stochastic processes in pure mathematics. They talk about supermartingale, submartingale, and the corresponding superharmonic and subharmonic functions. But the idea is just to drift it, to tilt a little bit, so that at the end times it reaches, for example, y. Start from x, it reaches y. So we are fixing it. That's why we call it bridge process. I mean, we want to steer the process, to control the process to hit a particular, so at time t we want to hit y. So for Brownian bridge, you can simply write this, because if you just substitute t equal to t, then what happens? It becomes 1, so it becomes y. It means that you have hit the target y, starting from any initial condition. And so let me explain this iterative Markovian fitting in 2023. As I said, it's a great paper, but it has computational complexity as well. But let's just review it in 8 slides. So we want to find a probability, a path measure that has at the initial point, at final time, satisfies these two distributions, like the image distribution and the blurry version of images. But at the same time, you want the KL divergence between a particular reference Q, because Q's it can be just simple Brownian bridge. It can be a simple distribution. And this Radon-Nikodym form in financial mathematics is very important. I mean, the theorems of Ito transform, Ito-Lemma, Girsanov theorem, and those things are very important for change of measure, because what you actually are doing is just you change a measure, and that transformation is the dupe, H. Of course, this is a naive way of looking at it. It's more profound than this. So what is iterative Markovian fitting? So we project onto space of Markov functions. We project the probability at iteration, the odd iteration, and we have, this is even iteration, this is odd iterations. So that even iterations, now, because you are changing the drift, it's a parametric. It's a parametric drift that, because it has some coefficients, so the next time that you want to simulate it, it becomes a little bit different. Because iteratively at different n, you have a different drift. So you do it forward and back for several times until, so if this path is the reciprocal class of Q, because any Markov class has Markov process has reciprocal classes. There are many of them, and also the Markov. So here, if this is the diffusion bridge, if this is Schrodinger bridge, then so it hits here, then here, then here until converges. The algorithm converges, and this paper proves that it converges if we do this. So they are learning the forward and the backward. Let's call it velocity, those velocity of forward and backward, in order to solve this Schrodinger bridge problem. So let's quickly review the losses in this paper. The first loss is just you're learning the bridge, you are learning the velocity of the backward. Another one is, so this is the learning the backward matching loss, because it enforces backward STE consistency with forward trajectories. And also, so backward loss, forward loss, these two. But there is another boundary that, because at the boundary it should matches pi 0 and pi 1. So you add the losses as well. So that's why we have 3 terms in our losses: forward, backward, boundary. The interesting thing, if you just write if you reduce backward drift from forward drift, it becomes this. So forward and so backward implements the global marginal constraint. So the goal of Schrodinger, what is the goal? We want the forward ST and the backward ST to say the same law. why is it hard? Because we also want, of course, to satisfy the initial distribution and the target distribution. So what can we do? You just write as a potential. These are phi and phi hat are potential of forward, potential backward. If you just reduce subtract the drifts of these two, forward and backward, it becomes very interesting, because the log of multiplications becomes a summation of the logs, so the final thing is that everything goes, and the only thing remains is that, of course, we know from factorization that this becomes the multiplication of this potential becomes your probability, and but it's hard to compute because it needs to solve that PDE, and if you plug 6 into 5, it becomes this interesting thing. So why this matters for the Fokker-Planck? The special case of Fokker-Planck is that continuity equations that become minus divergence of velocity times p, because if you don't have that volatility, the diffusion coefficient, then it becomes the continuity equation. And the forward, you write it. The backward of this Fokker-Planck, you write it. So if you subtract again, you get what we were talking about. So this is very interesting that it forces the forward and backward, if you want to satisfy that, the consistency, it needs to be, we force them to be equal. And so if forward velocity, if forward ST is this one, backward is this one, and so both STs must be flowing along the same family of densities. Again, an important thing about reverse time STE, if you just write it, you can see that the reverse STE is just simply this one. So what happens? B becomes minus B. Then what happens? Your diffusion coefficients becomes this one. This times again itself transpose. Now this is added to the drift, and this is again the diffusion part, but which is T minus S. But in this paper, they don't start with this initially. So you know all of these things. So let's start by the Q in Markov space, because there are many Markov processes. So the path measure, if we start from initial distribution, your X is drawing from your Q0, which is your initial distribution. Now the distribution of this process is pinned at initial and the target terminal point, because we know from the distribution of images and from the distributions of blurry images, of course it's a distribution, it's not a fixed point, so we can draw from the initial distribution. So under mild condition, this is a very important. The pinned process is a diffusion process that we can just write it like this. So using Dupe H transform theory, we can write. We define we can define the independent coupling like this. So this is a path measure. Whenever you see pi, it's a path measure, as I said. So we do not have access to V star, so we learn it. Like flow matching, we learn the velocity. We don't have access to that score, so we learned it in flow matching. Now is the same thing. So the interesting thing is, if your drift is just 0 and diffusion coefficient is just constant, then it's a Brownian bridge. so this is beautiful. You can explicitly write this. Just substitute t by t, then it becomes xt. If substitute t by 0, it becomes x0. And the intermediate zone is here. This is the intermediate zone. So in other words, it is forcing the Brownian motion to come back at initial level if your target is the same as the initial. So how do we learn it? There is an algorithm. First, they introduced a Markovian projection, which is just which is associated with this SDE, that we learn this velocity. You know the exact solution, but we learn it because we don't know Q. And the other one is reciprocal class. So you need reciprocal class, you need Markovian class, reciprocal class of Markov. Then the intersection is what we want. This is the Schrodinger bridge solution. So it is iterative. It starts with Markovian. It hits the reciprocal class of M. Then, because this is iterative, at odd time here, even time here, then after a time it converges to your here Schrodinger bridge. So we can write it like this. So in practice, we just use these two, but we don't know these two SDEs. That's why we have this algorithm that I explain it here like this, because here is the backward, here is the forward. So backward, forward, and there are two more important things. One, this one, the other one, this one. I have two slides for these two. Because what does it mean? You just get the endpoints after you simulate it. At each iteration, you learn a parameter. Then again, you get the endpoints, and the endpoints. The other one is your reference, except the endpoints. It means that intuitively you are trying to force the Markov process to satisfy initial and terminal conditions, the constraints that you want. And we call M the Markovian projection of your path measure using the learned V5. So as I said, I want to explain this term, what we mean by this. Because we use this endpoints plus the reference bridge, because we have a reference bridge, the first reference bridge that we mentioned. And so let me tell you what it is. M is the Markovian projection of the previous measure, because n starts from 0 to many time steps until convergence. And the Q is your reference bridge, meaning the conditional process given the fixed point. And pi 2n plus 1 is the new path measure. So what the formula does, first, so here is, we want a full trajectory distribution that has the same endpoints distribution as M, the same conditional dynamics between the endpoints. So we sample endpoints. As I said, we only need the endpoints, x0, xt. We don't need the intermediate. The intermediate is the same. These endpoints now encode the updated Markovian projection. So now that you have sampled, now that you have x0 and xt, just give it to your reference bridge, this reference bridge Q. Just give it to this reference bridge Q, and so this fills the full path respecting the original reference dynamics. So the pi here, after that, this one is just the full path measure over trajectories from 0 to t. But that path measure is very important because the marginals match the samples that you have drawn here. Remember, you first draw it, and then you go through the intermediate one. And also conditional paths given input follow the reference bridge